All right, so now we're going to look at an application within a word problem. So the top before the problem says if the vector u represents a force, then the projection is the effect that the force is acting in the direction of v. So if you're looking at a distance, it's kind of leading you to that distance. So it says, for example, if you push a box uphill in the direction or a car is going uphill with a force, the effective force is that push from v, and then it's going up in the direction, but it's got the force of u. That's that projection. So you're giving the same amount of force, but it's going to be at that angle. So what we're going to look at is we're looking at this 3,000-pound car sits on a hill, inclined at 30 degrees as shown, ignoring the force of friction. It's very important. What force is required to keep the car from rolling down the hill? So to start us off, the weight of the car is the force exerted due to gravity. So F equals the vector of 0, negative 3,000. Because we're looking at the car's going to roll down, so that's 3,000 pounds that's pushing it down, okay? So we want to find the force, which is negative W1, required to keep the car from rolling down the hill. So we're looking at the projection holding it in this direction when it wants to go this direction. So project F onto the unit vector in the side of the hill. First thing we need to do, we need to find the unit vector in the direction of the hill. How are we going to do that? Well, we are going to look at this because we have a right triangle right there, and we are going to go ahead and do the component form. So the component form, if you guys remember, that's v equals the vector, which then you find the magnitude of v cosine theta, and then the magnitude of v sine theta. So we found them separately, now we're putting them together. So in this case, our v is 1 because we don't have anything labeled as that. It is just our unit vector. That's what it states, unit vector v. It's just a singular 1. So that means we've got 1 cosine 30, comma 1 sine 30. So you may need to look at your unit circle. You may know this by heart, but that is root 3 over 2, comma 1/2. So that's vector v. So now we need to find the projection of F onto v. So we have F, which is 0, negative 3,000, and we have v, which is root 3 over 2, comma 1/2. So we first need to set this up. Dot product of F times v, those are our two pieces we're doing, over the magnitude of v squared all times v. So v is a unit vector, so the absolute value of v is 1. So this is actually over 1. So that makes it a little easier on us. We're doing F dot v, and then times v at the end. So let me minimize this. I feel like I'm saying so a lot. I apologize. So we've got, there it is again, but 0, negative 3,000 dot root 3 over 2, 1/2. So dot product of that, oh, and we've got the v on the outside, sorry. So dot product of F and v, 0 times root 3 over 2 is just 0. And then negative 3,000 times 1/2 is negative 1,500. And then that's times v. So the force required is, this tells us our projection of F onto v, which is our W1, if you guys remember. It's our W1. We need to look at our negative W1 because we need that opposite friction. So that means we're going to be looking at negative 1,500, which is just 1,500 v. So it's 1,500 times whatever the unit vector is. So it has a friction of 1,500 pounds, sorry, it has a magnitude of 1,500 pounds, and it's in the direction of the side of the hill. So that is that force that's required to keep the car up. So if you think about that, that's like you guys hitting the brakes on your car to like stop it from rolling down, or people are pushing 1,500 pounds worth of weight against the car so that it doesn't roll down backwards. All right, that's a word problem.